Welcome to this video on why does a dielectric increase capacitance. In the last video we showed that a dielectric does increase capacitance, but now we're asking the question why. And to make sure we're all on the same page, recall that a capacitor has a defined amount of capacitance because of a ratio of parts of its geometry times some sort of constant product between the type of material that fills the space between. So in other words, this specific ratio of the geometry is given for a parallel plate capacitor here. But this can be changed for a spherical or a cylindrical capacitor. This, however, on the side here is something separate than the geometry, because what this is describing over here is actually what we know as the dielectric constant. Now, the dielectric constant is proportional to how insulating, for lack of a better term, the material is between the plates. So this describes how insulating the material is, how good of an insulator the material is. Now, the epsilon naught is the vacuum permittivity constant, so really we're just multiplying that for each different insulator. Now, we know that when we put the dielectric into the space between, the capacitance increases. But we are not going to focus on that right now as much as we're going to be focusing on the actual relationship between the charge and the voltage when we have a dielectric present. So if we look at the definition of capacitance as the amount of charge stored per volt across the capacitor, let's say I have a capacitance with a value of 10 farads. If I want to store 100 coulombs of charge on the capacitor plates, I'd need to have at least 10 volts, right, in order to store that amount of charge, because the capacitance is fixed by these parameters over here. So in other words, what I'm saying is there's a dielectric in here, and there's certain geometrical sizes, and in order to store 100 coulombs of charge, I need to connect 10 volts across the capacitor. Well, what if there was a way to get the same amount of charge, okay, so we were going to fix the charge, but actually use less voltage. So we'll say a fixed amount of charge for less voltage. So in other words, it's kind of like a sale. I would get the same car, let's say, but for less cost. Okay, so what's going to happen here is ultimately the capacitance is actually changing when I increase this value. So if I increase the kind of insulator or the amount of insulation between the two plates, the capacitance actually goes up, and I can keep the same amount of charge and actually use less voltage because the capacitance has gone up. So just recall that this value over here is what is determining the amount of voltage needed for X amount of charge. So by adding a dielectric, what I'm essentially doing here is making the capacitance go to a different value so that I can keep specifically a higher value, so I can keep a fixed amount of charge and have this be a lower amount. Now I would only need 5 volts instead of 10 volts because the capacitance has actually increased. Now you might be thinking, well, yeah, you just put a different capacitor in, so it has a different ratio. 100% correct. We're just trying to highlight what would happen if we could change the internal material. Now let's take a look at how this process actually occurs. So I'm going to disconnect the battery here, and what I want to look at here is that the plate charge is now going to be fixed. So I'll go ahead and I'll put the leads of my multimeter, my voltmeter, across the two plates. There's nowhere for the charge to move anymore. So when I insert this insulator, the capacitance is actually increasing. Notice now that the plate charge is fixed, so it's 0.13 picocoulombs, or 0.13 times 10 to the negative 12 coulombs. And when I add the dielectric, I see I can maintain the same charge at a lower voltage. So let's look at what it was before. Right now, in order to have 0.13 picocoulombs, I have 1.5 volts needed across the two plates. But when I insert the dielectric, I see that I can maintain the same charge at a much lower voltage, at a 0.319 volt potential difference across the plates. So adding the dielectric actually allows for the same amount of charge to be held at a lower voltage. The reason why that's happening in terms of the numerical quantitative analysis is that the capacitance is adjusting when you've added the kappa value. But let's look at why the voltage actually drops. This is going to require us to look at the electric field. Always remember that the electric field and the potential of any location within the field, or the voltage, these are very closely linked to one another. If we have a constant electric field, we might write an equation that looks something like this. If we have a changing electric field, we'd have to write an equation that looks something like this. Okay, let's just focus on the constant variant for right now. If we look at this equation, what we're essentially saying is adding a dielectric, okay, so if I add the dielectric to the capacitor, it must be dropping the electric field because I know that the voltage across the plates is dropping. If I look here, I'm going to take a look at how that's possible to happen. The electric field between these two plates right here would of course be pointing straight down. So let me go ahead and sketch that out over here. So if I have my top plate, which has a positive charge, and I have my bottom plate, which has a negative charge, we're going to ignore the fringing or the edge effects. So here's my positive charge, my negative charge, and I have something that looks like this. Now I'm going to name this electric field E sub naught, okay? And this is going to be one that you can think of as the external electric field to the dielectric. So right now there's no dielectric in here. Take a look very closely here at these little positive and negative charges which are superimposed on one another right now. If I only show excess charge, what I'd see is that there's no excess charge in the dielectric. In other words, it's neutrally charged. It's also an insulator, so electrons are not really free to roam around. However, in the molecules or the atomic structure of each of these little regions, the electrons can be sort of distorted one way or the other. So if I insert this into the electric field that's already there, I notice that a little bit of polarization, which we can call localized polarization, has occurred in each of those little regions. So what I'm going to do here is I'm going to draw in how this has occurred. So the electrons have been attracted to the positive plate, leaving the region just below them as being positive. And so I get something that looks a little bit like this. Keep in mind, we're not having a whole polarization of the material, just these little local regions. But every little local region is going to set up its own little mini electric field, which I'll call the electric field in the dielectric, so E sub D, like so. Now I can think about adding those together to get the electric field like this. Now this is not going to be a very strong electric field compared to the external or the capacitor's electric field, but it will be something that is opposite in direction. So if I want to figure out the net electric field now between the capacitor plates, what I'm going to do is I'm going to say my original electric field plus my dielectric electric field, which is negative, will result in my new electric field, which I'm going to call E prime. So E prime is the electric field when the dielectric is present. So when the dielectric is present. Now keep in mind, this is a net electric field that combines the individual electric field of the dielectric and the original electric field of the capacitor. Now this electric field over here is not present unless it's inside the capacitor field, right? Because if you see, if I pull this out here, obviously I'm eliminating the electric field that's making the polarization occur in the first place. So we can see that by adding a dielectric to the capacitor, I end up dropping the amount of electric field and therefore dropping the amount of voltage that's needed. Now, what's causing that to happen is the increase in the capacitance, right? We're looking at it from the back end, even though on the front end, what you're really saying is, I'm putting in a material that makes the capacitance a larger value, thereby I can store the same amount of charge as I would with a lower capacitance, and therefore it can be at a lower voltage, because this ratio will have to always equal the value of the capacitance. So the chain of events can be seen as related to what we talked about before. When you attach a potential difference and you create a potential difference across the conducting path, we'll have a separation of charge. That separation of charge will construct an electric field or a potential difference and then an electric field, or vice versa. That strength that's needed to separate the charge is here lowered or depleted by adding the dielectric constant. Some other practical reasons we'd want to add a dielectric constant is actually so that we can have the plate separation be narrower, right? So we can have much smaller space here in between, and in doing that, we'll have less chance of the two plates touching each other, which would cause a shorting or what's called a dielectric breakdown. So you can force the capacitor to have so much potential across the plates that it will actually break through the dielectric and it will cause sparking or shorting between the plates as the potential energy is increased drastically. Another reason that we would have this insulator in here is also to provide some sort of barrier for the plates so that they can't physically touch even if they were more separated. Once again, to prevent the passing of electrons through this space. After all, when we have a capacitor, we want to maintain the difference so that we have potential energy here, rather than allow the two to come together and touch, which would deplete the amount of potential energy that could be used to do other things in a circuit. So hopefully this gives you a little bit of a reason why the dielectric, adding it to a capacitor, increases the capacitance, thereby decreasing the amount of potential needed to achieve the same amount of charge separation.